So if you've taken a physics class, you probably learned about energy and the conservation of energy. And that word conservation, it might have come to mind when we talked about conservative vector fields. And there's a reason for that. The naming actually goes the other way. Conservative vector fields are called conservative because of conservation of energy and not the other way around. And I wanted to show you what the link is. So the scenario is this. Let's suppose we have a force field. So our vector field is playing the role of a force in this situation. And it happens to be a conservative force with potential function F. And also we have an object that moves around along this curve R only under the influence of the force F. Okay, now this is going to be a key thing, only under the influence of the force F. So the only force acting on this object is the force that is the vector field, capital F. Before we get started, a couple notes on some physics terminology. So in this kind of scenario, there are two kinds of energy that an object can have. One is kinetic energy, which is just the energy that something has by virtue of its motion. And it turns out that the formula for kinetic energy, which I won't justify, it turns out it's 1/2 times the mass of the object times the square of the velocity of the object. So 1/2 mv squared is kinetic energy. But by the way, we're assuming we have a constant mass here. The object that's moving around has a constant mass. If you have an object that's shedding mass somehow as it moves, things get a little more complicated. Not that much more complicated, but a little more complicated. Anyway, so that's one type of energy, kinetic energy. Another type of energy is called potential energy, and it has something to do with the force. So where the object is located in the force field. And potential energy, the symbol I'm going to use for it is phi, this lowercase Greek f essentially is what this is. And the formula for it is just the negative of our potential function f. So it's a little confusing that there's this minus sign here. You would think potential energy should just be equal to the potential function, but that's not the case. The reason that physicists put this extra minus sign here is so that the force coming from a potential acts in the direction to decrease the potential energy. So that's why they have this minus sign. Physicists like forces to decrease potential energy. So the upshot of this is that our force is the negative of the gradient of the potential energy function. If you're in a physics class, you do have to be careful because I think physicists will just say the potential and they will mean phi, not f. So got to be careful. Also, I think often physicists, when they say gradient, they will mean the negative of our gradient. So got to be careful. Anyway, so in this situation, what I'd like to do is see what happens to these two quantities, kinetic energy and potential energy, as the object moves through some interval in time. So let's say that t is going to go from little a to little b. And just to name our starting point and ending point, let's say that at time a, so our starting time, our position is capital A, and at our ending time b, our position is capital B. Just so we have the names for our beginning and ending time and our beginning and ending position. Okay, so to get things started, first let's figure out how much work the force does on the object as it moves. Remember, the expression that we got for the work a force field does is just the line integral of that force field along the curve. Okay, so let's compute this. Now there are a couple ways to compute this. One way is just to remember that the force is related to our potential function. So this is minus integral over the curve of the gradient of phi dot dr. And then use the fundamental theorem of line integrals. So the fundamental theorem of line integrals says that this is the negative of, so we do our potential function, our potential energy function at our ending position, which is B, minus our potential energy function at the starting position, which is A. And then this minus sign just flips the orders. So we get potential energy at A minus potential energy at B. Okay. But there's another way to figure out or to express what the work is from this line integral, which is using the fact that this object is moving only under the influence of the force F. If the object is moving under the influence only of the force F, then that means that it has to follow Newton's second law. I mean, it always follows Newton's second law, but we can account for Newton's second law because we know all of the forces acting on the object, because there's just the one force. So Newton's second law says F equals ma. Well, it says that the total net force is equal to ma, but we only have the one force acting on this object. So F equals ma, but since in this situation, a is the second derivative of r, right? Acceleration is the second derivative of position. So another way to express work, which is again the line integral of f dr dot dr, this is an integral of f dot r prime dt. And sorry, I should have my t bounds here from little a to little b. Well, using Newton's second law, F is m times r double prime. All right, and then dot r prime dt. Now this product with one thing differentiated one more than the other, there's a nice trick you can do here, which is, so when you took Calc 3, you probably worked out as an exercise what the derivative of r prime dot r prime is, right? Well, you use the product rule, right? The dot product follows the same product rule as in single variable calculus. So you get r double prime dot r prime plus r prime dot r double prime. But the dot product is commutative, so these two things are actually equal to each other. So this is 2 times r double prime dot r prime. But look, that's almost what we have inside this integral. If we move this m outside, and we need a 2, so to get a 2, we also have to divide by 2. So let's divide by 2 there and multiply by 2 here, r double prime dot r prime. So other than shuffling the constants around, right, this is the same thing as the previous line. But now this thing that we're integrating is actually just the derivative of r prime times r prime, or dot r prime. So this is the derivative with respect to t of r prime dot r prime. But r prime dot r prime is, so into m over 2 times the integral from a to b, derivative with respect to t, r prime dot r prime, that's the magnitude of r prime squared. That's what you get when you take a dot product of something with itself. And now we have an integral of a derivative. And the fundamental theorem of calculus says, if you do an integral of a derivative, what you get is, oh, well, I guess first of all, before we do the fundamental theorem of calculus, notice that this magnitude of r prime squared, that's the velocity squared, right? So now when we do the fundamental theorem of calculus, what we get is the velocity squared at B minus the velocity squared at A. Okay, so this is m over 2 times the velocity at B squared minus m over 2 times the velocity at A squared. But this is just the kinetic energy at B minus the kinetic energy at A. Okay, so now we have two ways that we wrote down the work over this period of time. On the one hand, it was what we just got, the kinetic energy at B minus the kinetic energy at A. But on the other hand, remember, we also figured out a way to relate it to the potential energy. We found that it was the potential energy at A minus the potential energy at B. Now, if we rearrange things, if we move this kinetic energy over there and this potential energy, we get potential energy at A plus the kinetic energy at time A equal to the potential energy at position B plus kinetic energy at B. But look, this is over here on the left, we have initial total energy. And on the right, we have the final total energy. That is the total energy at the end of the motion. So what this is saying is that if you have an object moving around under the influence of a conservative vector field, total energy is conserved because it's the same at the beginning and at the end. And this was true for any interval of time, so that means energy is always conserved in this scenario. So this is why this is one reason why conservative vector fields are important, and it's why conservative forces are so nice when you're working in physics situations. Now, as far as we can tell, all forces, all of the fundamental forces in the universe are conservative, which means that energy is conserved universally. There are some caveats to that involving general relativity, but at least in special relativity, energy is conserved. In physics situations, the most common non-conservative force is friction, but friction is just a name that we give to a very complex situation involving the electromagnetic force, right? Some energy sort of leaks into some small scale structure involving the electromagnetic force that we can't detect on a macro level, and we call that phenomenon heat. So that energy, the energy that we lose due to friction doesn't disappear. It actually just sort of goes into a place where we can't see it. So energy is actually conserved in basically any situation.